Okay, good late morning, everyone, and I am so glad to see there are still people in the room. We actually had the second to last session originally, and then due to a conflict, we asked to move, and they didn't move us earlier. We got the last slot, so note to self. If you notice here, first of all, I'm Deborah Smith. I am the lead of NASA's Airborne Data Management Group, which has been recently spun up to help with getting airborne data more discoverable, more usable, and to work a lot with the airborne data scientists to keep them happy and feel like they're getting attention, and making sure that we aid their science as much as we aid the satellite team science. So one of the things we're doing in addition to this session here at ESIP is other sessions at AGU. I'll have some information about that later. But also I work with each of the current EVS3 teams to assist them in developing better data to go to the DACs, and then also working on an airborne data inventory that will record all the airborne campaigns of the past in NASA. And some are published and some are not, so it's a little bit of data recovery in a way. So we have the session on improving airborne data discovery and use, and we have several goals as stated in the Schedule description. My co-conveners, who I couldn't have done this without, is Amanda Leon from NSIDC and Helen Conover from UAH-ITSC. And we have a little bit.ly down here for a notes page if you are so inclined to assist us in recording thoughts and discussion items. We would appreciate it. Uh-oh. Down here, I guess. There we go. So airborne observations are typically collected by aircraft flying along within an investigation that is not just about the airborne, it's also about usually ground measurements in support of that airborne and satellite measurements in some form of validation. It's very intensive, lots of measurements on lots of instruments on those aircraft and collecting lots of different kinds of measurements, and all of that needs to work together because this entire thing is focused on studying some geophysical feature or physical relationship. So it makes for a different kind of collection of data than a satellite data that we typically see people working with. It has very irregular spatial and temporal coverage, which can make it difficult to describe using metadata conventions and to work with. There's diversity in spatial and temporal scales. You have cases where instruments are going on and off, or they might fly one flight but not the next because they failed soon after takeoff. So there's a lot of information that's needed, a lot of metadata that's not typically collected and reported. And if we get all that metadata, if we sign that now, we have a lot better ability to work with the data. So the diversity in spatial temporal scales is also in coordinate systems, variables, data formats, and it makes it difficult for all this data to be used together, but indeed it has to be used together because it's studying some geophysical phenomena. So compared to satellite data, airborne data is typically much smaller, and it has a smaller user community. So it's not, these are not large data sets. They might be, part of the investigation might be a ground radar, and that can be a large data set. But a lot of the actual airborne data set is not very large. So we're not talking about a problem of size, we're talking about more of a problem of, we've got a small user community, and that's, why is that? We're going to be looking at that today, and how we can change that. And the community typically is those researchers involved with the campaign, and they do it for a short period of time before they move to the next campaign, and then the data sits in the archive. So the question is, what can we do to help change all of that? Some of the solution spaces that have been identified that might help with making changes is improved metadata, both in geographic as well as other descriptive metadata. as we were in the, I don't know if you were in the last session, was talking about how do we spatially name things so that we can search by region. For instance, if an airborne campaign studied the Appalachian, North Carolina region, we would want to describe that as part of the campaign metadata. But what does that really mean, and how do we represent that? And how do we use standard terms to do so? Also looking at standard data formats to use. Typically, the airborne community has used their format that they've kind of iterated and evolved to, in this case, ICART, and then also the drops-on data being in the drops-on sounding data being in ASCII files of a particular format. So how do we deal with that? And maybe Ted will speak up today talking about, taking mid-bite, talking about ICART to ISO, which he's working on. Also, we have if we could improve the tools, improve the search results when we're working with airborne data, exploration, visualization, and analysis of this data. And then lastly, is really important to work on improving communication, and that includes education and outreach, describing the data better, raising awareness that this data exists and what you could do with it, and as well as demonstrating use of the data. I don't want to leave out metrics. One of the important things is that any effort we put into change and helping to improve airborne data use probably needs to be documented because of the fact that we're going to be putting a lot of effort in, and how much gain are we going to be getting out. So it's got to be part of the conversation, and metrics can help us identify where's our primary problems and how do we prioritize what might work most and work on those effective solutions. So one of the things I'm really interested in is, what are we doing now in different communities to identify information about data use? Who's tracking how much of this data is used? In the case of NASA, each deck may be tracking its download of airborne data, but collectively across all decks that is not performed, and we would like to see that performed. So also, what do we need to better understand airborne data use, data issues, and needed improvements? And here we ask, can we learn from download metrics can we learn more from download metrics with some changes to those metrics? Can citation metrics allow us to tease out use by the original science team as compared to the broader community usage? And will that tell us, is that data going beyond just that team? And how can we tell if users from various communities are getting what they need and what novel approaches can be reasonably implemented in the role of metrics? Especially important is to collect metrics now and then collect metrics later and see if whether all our efforts are making a change. So we've devised a session today. We've got some speakers. We're trying to keep this to a high level, not get too far down into the weeds. We have 3 speakers from different domains representing geophysical features and physical processes that are studied. And today we have hurricanes, snow and ice, and ecology. And then we have one speaker who's going to demonstrate some technological tool changes for better airborne data visualization and exploration. And then we're going to follow that with a little group discussion. We'll break into 2 groups. I think we're going to, it's good size here. And then discuss a series of questions and then come back together and see what next. So of the after speaker discussion, and we're putting this out to you now so that you can think about it as you're hearing the speakers. We're interested in teasing out how do we build interest in and a community around airborne data that's more vocal and can address the issues more. We also want to look at identification of problems and how do we identify them? Is it more than just a grumbling of people who are trying to use the data? And then how do we prioritize those changes that are needed? Metadata and tool improvements that would really help. And then that effort versus outcome threshold. How much effort to what outcome is worth it? And then what's next? So with that, we'll jump right into our first speaker. We have Heather Holbach, who's a postdoctoral scholar at HRD, Hurricane Research Division in NOAA, and she's going to enlighten us about the issues with airborne data in hurricanes. And getting to it. Do you guys know, I didn't see before what you were doing, where all the slides are? No, thank you. Yeah, they're all right here. Perfect. There we go. Thank you.
Great. Well, thank you very much for the invitation to come and speak with all of you here. This is my first ESIP, so I'm really enjoying all of what I'm learning and look forward to collaborations in the future. So about 2 years ago, we formed a group within HRD to get a better handle on the status of our data and what we need to do to help improve the way that we manage our data. I co-lead our data management group with John Swislak. And so let's see. So first I want to start out giving you a little bit of information about NOAA's Hurricane Research Division. So we're a group that's primarily focused on research using observations, improving modeling and data assimilation. And so we have experts within this division on all three of those topics. And working with each other allows us to improve our understanding and prediction of hurricane intensity, structure, and hazards. And one of the unique things about our division is we have access to an annual hurricane field program. So every year we develop a field program plan, and we to target answering specific questions about hurricanes and their formation and anything of interest in regards to testing instruments. And so every year we go out there and we collect all sorts of data. And we have 2 aircraft that we use for doing this. We have a jet, the G4, and we have 2 P3 Orion aircrafts who are our workhorses and fly directly through the storm. So we've gathered a whole bunch of data in support of research, but we also support operations. So we have a pretty varied user group within the tropical cyclone community. So on the left, you can see all the information about our research flow, but this connection with operations is really important for us. We get feedback from the operational community as to what types of questions they have that we can then perform research on and answer and then feed back to the operational community. But we also work with modeling centers to gather data in real time for them to ingest into their models. We also work with the forecasting centers like the National Hurricane Center and the Central Pacific Hurricane Center to get data for them in real time as they're analyzing the storms that are occurring and to help with their forecasts. But we also support relationships with NESDIS on the satellite side. So we do efforts to help with satellite validation. So we have a large variety of different types of observations that we make with our aircraft. And with these come a whole lot of different file formats and types of data. So we have our observational data, which are listed on the top of this list, but we also have documentation about information about the storms and the missions that we've flown. On each flight, we maintain logs that are handwritten. We're trying to transition to electronic for those, but it's a slow process because of capabilities on the aircraft. But we also have all sorts of numerical model output. So trying to figure out how to manage all of these different types of observations and documentation and model output is quite challenging for us and something that we haven't done enough with or kept up with over the years. We started collecting data with the P3s in 1977. So we have a pretty long historical record. We actually have data from other aircraft going back to 1960. So this is a very large data set with a vast amount of information that we need to make sure is preserved and made easily available for users to get the most out of it so that we can learn as much as possible and implement into operations to get the best forecasts to help protect life and property when storms are threatening coastlines. So here I've got a couple of examples of the types of data visually. So we have time series of data. We also have, most of our data is track-like data. So here you can see an example of our flight level winds. But there's a lot of other variables that are along this same track. We also have vertical profile data, like our dropsons. This is a plot showing all of the dropson locations in a storm relative sense that we've released since 1996. So there's a lot of them. But we also have a unique instrument in our planes that gives us a 3D picture of the reflectivity and wind structure of a hurricane. So this is probably our most challenging data set to figure out how to deal with, since it's three-dimensional. But this is just showing a cross section of what we can get from it. So we've got a lot of really important data that's got a lot of different dimensions and variables and temporal and spatial resolutions that are tricky to deal with. Right now, our data can be accessed through a public FTP server and through a web-based portal. It's pretty clunky and outdated and something that we're very much looking forward to improving. So right now, our data is separated by year, storm, and then flight. So it's really challenging to go into our data on the public FTP and pull out, say, all of the data for a specific instrument, or all of the data even for one flight, since it's all separated by these different criteria. And most of our data is lacking in metadata. So that makes it challenging to move forward until we can add this metadata to help with the subsetting. We also have limited updated documentation. There is documentation scattered throughout our site. Most of it hasn't been updated since it was first written. And so it can be very challenging for our users to understand how to appropriately use the data, and even for us who work at HRD to know how and the most updated information on some of these data sets. And for us, we're focused on the research quality data. Our partners at the NOAA Aircraft Operations Center are responsible for the raw data, so we have to work very closely with them in identifying the responsibilities for each of our organizations and to make sure that everything is covered and taken care of appropriately. But we also have other partners who put instruments on our aircraft that we don't take responsibility for, they take responsibility for. So trying to figure out how to make sure that users are aware of everything that's available for our flights has been very challenging. And then we also maintain some of the data from the Air Force Hurricane Hunter aircraft, but we have a very large delay in getting that data from them, sometimes because of the limits that they have on their end. So the time delay for availability of these data sets is quite varied for all of the different instruments, and especially depending on where they're coming from. So another effort that we're really trying to focus on is real-time visualization of our data. We want to make sure that people can see what we're collecting and what we're seeing as soon as possible so that they can get the most benefit out of it. So right now, most of our users rely on going to third-party websites. One of the popular ones is Tropical Tidbits right now. And so we want to, make sure that people can come to our website, since we can link them directly to the data and to, in the future, better documentation on the data. And we also can provide the context for the data through our mission documentation. And the overall goal is to, provide insight for flight planning and rapid response research. So data is becoming more and more powerful, and we want to make sure that we can get it available in a way that's easier to identify types of questions that they might be able to answer with our data. So here's a couple of new graphics that I've been working on to help integrate some of our different data sets in a way that is helpful to answer some questions, but we want to get to a more interactive interface where users can select what types of data they want to compare together and to see what kind of questions they can answer. So far I've focused primarily on the purely aircraft side, but we also work a lot with the satellite community, and the satellites contribute a much larger amount of data on hurricanes. So it's very complementary to our data. It's really hard to have an aircraft out there all the time. So you get these gaps in the data. And so satellites help to fill those gaps. And so trying to figure out how to better integrate our aircraft data with satellites is a big challenge for us. We also try and coordinate underpasses of satellites for validation efforts. And so improving the way that we are able to integrate our data can really help us with these efforts as well. And so oftentimes in a research mode, we also want to know what satellite data was available that coincides with these aircraft. So this data integration is going to be really important for the future in helping with research. So I'm going to finish up here by summarizing some of the challenges we've identified and some of the potential solutions. So our first big challenge that we've been undertaking is trying to understand who our users actually are. Are they just researchers, or do we also have students and teachers and the general public trying to use our data? And we put out a survey about a year and a half to 2 years ago, and we found it very difficult to get people to respond. And so trying to gather a way to understand our users better is really important for us. And as I mentioned, our data accessibility is very challenging right now. In the future, we would love to be able to offer the ability to download anywhere from data from one storm to an entire historical record. So getting our data set up in a way that makes this easier would be very helpful and beneficial. Our instruments change with time too. So trying to find a way to alert our users to when these changes happen, or we don't always have the same setup of instruments on our aircraft each season or even throughout the season. So making sure our users are notified of these is also a very important thing. And then we have a pretty long historical record that needs to be treated similarly. And so that's also a pretty big challenge for us in trying to identify, how to best approach that. We have all different formats, spatial and temporal scales. This goes hand in hand with the previous bullet. And so trying to figure out how to integrate these in a way that makes it easier for users is a challenge. When comparing with satellites and even different instruments on our planes, they all use different techniques to observe the same quantity. And so trying to figure out how to compare those and make sure the users are aware of those differences is very important as well. And then going along with who our users are, what do our users want to do with our data? Are they primarily using it for decision making or assessing data or for research? And the answer to those questions is really important into what sort of data quality we provide, or with the latency needs. So if people are trying to use it for decision making, maybe they don't want as high a quality if they can get it sooner. And so understanding these really makes it helpful to determine what we need to do as data providers. I would say one of our biggest challenges right now is we don't have a dedicated data manager. We're all scientists trying to do this. So we don't have the expertise that we need to be able to do the best that we can with our data management. Right now, John and I just care a lot about data. So we've, volunteered to take on the first steps in trying to push this effort. So I think we've determined that we definitely need some more help. And then one of the other questions that we need to answer is, are we a data center? And the answer to that will really help guide what we need to do in the future as well. So as far as some of the solutions we've identified so far, one of the first steps we took is we developed data management plans for all of our data sets. And that's really helped us get a better grasp of what the current status is of all of our data sets. So that's been very helpful. In the future, our goal is to work with NCEI for archival, and that'll help us with maintaining our data sets. We've started using program savvy students to help us with new ideas for visualizations. And then we want to modify our data so we have better metadata with it that makes it easier to work with. And we want to be able to allow for science question driven data mining by revamping our architecture and offering visualizations, getting serious about metadata, linking to other data sets, and integrating with other data sets. And this is a very evolving task, and we're trying to set some 1 year, 5 year, and 10-year goals to help with this effort. So thank you.
Is that working? Yes. That was really helpful. I know of your data, and I've been always wondering, is it just the scientists doing it? And clearly that is the case. So it's a very valuable website that I've used over the years many times, and a lot of work there. Any questions?
Thank you very much. This is Nisha from the NASA Goddard, just this data center. Actually, we probably can share some experience with you. A few years ago, come up with called a Hurricane Data Bundle idea. And then we end up with now it's called a Hurricane Data List. What we do, because as a hurricane scientist I did before, I know when I study hurricane, I know I need to a wind field, I need a temperature field, all kind of field, right? And how we are going to help those scientists, those users, to go to our stack to find those data set. So we really come up with a data list. We already prototype one case, exact using hurricane one. Maybe I can share with you some experience offline.
Yeah, that'd be great.
Thank you.
Thank you for the talk. You mentioned that you have a lot of handwritten logs that are still being undertaken. Have you figured out some approaches to make it possible to do digitized entry, something that's actually approachable to pilots or scientists that are in the field?
So we're trying to move to fillable PDFs on the aircraft. But as far as the logs that we already have, we have no idea how to do that, to digitize those. I mean, we scan them in, but actually moving the handwritten to digital, we have no idea how we're going to handle that.
Thank you. Thank you, Heather. We have to move on, but we're going to have a discussion period so we can even bring up more questions then. Next, we have Tristan Golden from,
From Neon.
from Neon.
From
Yes,
Neon, yeah.
thank you. Right. Perfect.
Yeah, thanks. So yeah, my name's Tristan Goulden. I'm the science lead for the Airborne Remote Sensing Group at NEON, which stands for the National Ecological Observatory Network. For those of you who may not be familiar with NEON, this is in essence the observatory. We've divided the continental US, Alaska, Hawaii, and Puerto Rico into 20 unique ecoclimatic domains. In each one of these domains, we have 2 to 3 sites where we conduct observations. And so the intention is for the observatory to do continental scale research over a long temporal period, because the observatory is intended to run for 30 years. So the schematic shows kind of the different sampling efforts that might be occurring at a site. So we have instrumented systems such as flux towers for gas exchange, also measuring temperature and pressure, as well as instrumented systems measuring water quality. We also have observational systems where we have individuals measuring information about vegetation, small mammals, insects. And of course, we have the Airborne Observation Platform, which you can see as the plane, which is what we're going to focus on today. So the Airborne Observation Platform collects airborne remote sensing data, and we're covering a regional scale, normally a minimum of about 100 kilometers squared. So as Deborah mentioned, this is very much a system that is a go-between between the field measurements that are occurring at the sites and satellite measurements that measure across the entire continent. The data products are generated at what we consider high spatial resolution, less than or equal to a meter squared. And we have 3 primary sensors: a waveform LiDAR, imaging spectrometer, and high resolution camera. So this is an image of our remote sensing payload. On the far left, you can see the imaging spectrometer. This was custom built for us by NASA JPL. And then this little green box on the right is the waveform LiDAR, and then next to that is a high resolution camera. And so we actually built out most of the support and electrical infrastructure that integrates these 3 sensors. And we actually have 3 of those sensors, 3 of those identical payloads that we operate on 3 different aircraft. This is a typical example of how we would fly one of the NEON sites. So this is Harvard Forest, which is in domain 1 in the northeast of the US. The white boundary represents the area where field sampling would be occurring, and then the red dot is where the flux tower is. Normally, we'd like to center our flight box on the flux tower and have that minimum of 10 by 10 kilometers. We also want to make sure we cover the primary airshed of that flux tower, and we never want to go have our area less than 2 kilometers from the center of that flux tower. So normally then, to be more efficient, we'd shift this box over. But then we also want to capture the rest of the sampling boundary. We'd extend that box, put down our flight lines, which are in a north-south orientation, and then we would just fly these lines sequentially, kind of like mowing the lawn. The swath width of the aircraft or of the instruments underneath the aircraft is about 600 meters wide. So we just sequentially fly these lines until we've covered this entire area. And then we generate some really nice imagery. So this is a LiDAR point cloud of a forest stand, and you can see on the left-hand side, it's colorized by the height of the trees, so we get that nice rich structure of the vegetation. And on the right-hand side, I've colorized that point cloud by the visible bands of our imaging spectrometer. But of course, we get this much richer information because we get that full spectral response from the vegetation that goes from 380 nanometers out to 2500 nanometers. From that, we generate a series of data products. We separate those into level 1, level 2, level 3, similar to NASA, where level 1 is kind of the most raw form of data that we have. And then we derive those higher level data products with some type of processing algorithm. So level 2, for example, is primarily vegetation indices from our imaging spectrometer. And then level 3 is also those vegetation indices as well as LiDAR products, but provided as mosaics tiles, 1 kilometer by 1 kilometer tiles, as opposed to level 2 products, which are our flight line. This kind of represents what a typical year of data collections looks like for NEON. So this is our 2019 schedule. You can see I've colored each of the domains by which payload is going to be flying that particular domain. 2019 is a little bit differently because normally we cover all of our intended domains with 2 payloads, but we added the 3rd payload this year to add some extra capacity. And so normally we would try to fly each domain 4 out of every 5 years. Just for some historical context, this is how many times we've actually flown each domain. So you can see for several domains, we're actually starting to get a really nice time series at those domains with 5 years of collections. This is kind of the life cycle of our data. We will, go out and collect. We have hard drives located on the aircraft that record all of that raw data. And so we also carry what we call a hotel kit along with the aircraft, where we'll take the hard drives from the aircraft, put them into the hotel kit. The hotel kit will do the extraction and some level 0, so raw data quality checks automatically. And it'll actually ship those, download the data off the hotel kit, ship those drives to our data center in Denver via FedEx, and then upload that L0 or raw data to our data center, into our archive. And our scientists at headquarters will download that data and then execute our processing pipeline to generate all those higher level data products, which we'll then put back up to the archival system and then connect with the data portal. And then people will be able to go to the Neon data portal and download those data products. So what are some of the data challenges that we have? Okay, I'd be remiss if I didn't talk about some of our data collection challenges. And most definitely, weather is by far our largest data collection challenge. We can't fly the instruments if there's clouds below the aircraft, because obviously it blocks the view of the sensor. And the data quality of the spectrometer is severely affected if there's overhead clouds. And so this image you can see is actually from just south of here. We just finished our collections in our D16 sites, which are near Portland. We were there for 3 weeks, and this is what we experienced for the entire 3 weeks. So we actually didn't even complete our collections in that domain this year. Oftentimes, even if there is overhead clouds though, we will still fly to collect information with the camera and the LiDAR, because that information will still be good if the clouds are just overhead. We also try to collect our data in periods of peak vegetative greenness, and this is to control for the phenological cycle, changes in the phenological cycle through each collection year. And so we've actually done a historical analysis of when peak greenness will be at each site, and then collect data during that time period. Of course, when you combine this peak greenness constraint along with the weather, it can offer really challenging circumstances. For example, in Great Smoky Mountains, typically what we'll find is that the worst weather occurs there at the time that peak greenness is also occurring. And of course, we can have sensor failures, and often we may have to fix sensors mid-season. We also have challenges with data volume. Currently, we're holding about 150 terabytes of information with 80 terabytes of intermediate files. We anticipate collecting over 100 terabytes of data per year. Of those data products, the at-sensor radiance, waveform LiDAR, and reflectance represent the vast majority of that storage space, which is our L1 products. So it's a challenge to get this data to our users, particularly to a user group, the ecological community, that isn't used to using data of this volume. And I just threw in a notable file formats there where we have 2 data products or 3 data products, these radiance, reflectance, and waveform LiDAR, kind of in non-standard file formats that we have to get or educate our users on using. We also have challenges in latency. In 2013 through 2018, it typically took us about 3 to 12 months to get our data from collection out to the users and available to them. For some people, this can be a really long time, particularly students who may be doing a master's project and need this data on a much quicker schedule than we were initially releasing it. So we've actually overcome this challenge in 2019. We're striving to publish our data 60 days after our final day of collection. You can see in this table, these are some of the sites we've collected already in 2019 and the number of days it took us to publish those data products. So we're nearly meeting that 60-day requirement. Of course, what we're also running into now is issues in republishing data when there's algorithmic enhancement. So right now we have the capacity to kind of handle the data that's coming in each year, but it's difficult for us to then reprocess the entire archive if some algorithmic enhancements come in place and we want to improve the data products. Also some data challenges in QA/QC. So always our top priority is maintaining the accuracy and the fidelity of our sensors, because that ensures quality of our L0 data stream. We always have the opportunity to go and reprocess higher level products, but it's critical to us to maintain that L0 data stream. And so always that's our top priority. We have a limited capacity to have eyes on all of our published data. We're producing a lot of data with a fairly small team, so it's impossible for us to look at every single piece of data that we publish to the portal. We develop automated QA checks as best we can and monitor those and hope that that's going to catch most of the mistakes. We also rely on commercial off-the-shelf software from vendors for some of our data products, particularly the Airborne LiDAR, where we're using proprietary formats from those vendors that only their software works with. You can see the images on the right. This is a point cloud where the bottom image is what the data is supposed to look like, and the top image is what the data started looking like after the vendor made an upgrade to the software. And it took them about a year to fix this. And so this obviously affects our latency and our ability to produce those data products. As well, communicating uncertainty and limitation of the data to the users. And then what we've recently found is evolving with cutting edge science. And so a lot of the algorithms that we have been using were produced, over a decade ago, because that's when, the observatory initially sort of decided on a lot of the different algorithms that would be in place. Over that time period, we've seen a large change and advancement in airborne remote sensing. And so now we're also have just gotten up to speed with producing this data, and we're also at a time where we need to start upgrading those algorithms to sort of produce the most cutting edge and best data products we can.
Other questions for Tristan while we switch speakers?
When you were talking about, I'm gonna walk and do this, the latency of production, I was just curious, what were some of the reasons for the long latency, and then how did you address those to be able to start processing with the 60-day window?
Yeah, so I mean, as enhancements in our processing pipeline, the efficiency of the algorithms that we were using, as well as, over this past year in 2018, one of the primary delays was that the archival system that we didn't have a good schema for controlling how that data was uploaded. And so we were developing that over the past year. Now that that's finished, we're able to get that data sort of properly organized onto that archival system.
I have a question, Tristan. Sure. Do you have a sense of, is your community of users primarily one community?
Sorry?
Do you have a sense of your community of users? Is it broad number of users, or is it just primarily the vegetative community?
Yeah, it's interesting because, I mean, the observatory is designed for the ecological community, but certainly, near to the beginning of when we started producing data, we had a lot of just remote sensing scientists that were interested in the publicly available data. And so, but I think that's starting to transition now to more of the ecological users.
Thank you. So next we have Jeff Deems from the NASA Airborne Snow Observatory.
Good afternoon, everyone. Thanks especially to the previous two speakers. It's somewhat gratifying and yet frustrating to hear that we are all suffering a lot of the same issues. So I want to start off by saying what they said and hopefully build on that. And in that light, I want to thank the organizers for helping further quite a necessary conversation here. So a little bit tongue-in-cheek with my title, but a lot of times in data management, we look to an existing process in order to adapt a new one. And airborne data seems to match a lot of the criteria or what we recognize in satellite missions or ground-based missions, but it's a little bit different, and we end up applying techniques or processes to these data that were actually designed for something else. So I think it's really important that we're considering airborne data separately. So just briefly, I'm going to give you the first couple bullets here, just dive in a little bit to the particular needs and generation of the Airborne Snow Observatory and its very operational focus, and then back out a bit and talk about some of these problems more generally. So the primary issue that we're facing with the Airborne Snow Observatory is hydrologic forecasting, so and in snowmelt systems. So this is wintertime snow accumulation, spring and summertime melt-off providing water supply. We're focused on the Western United States. So this is 80% of the water supply in the Western US is snowmelt. And there's two basic types of operational forecasts. One is a total runoff forecast, so an April through July volume, aggregate volume, and that is generally conducted by regressing April 1st water equivalent measurements from a station network on stream flow with a 30-year minimum period of record and saying, okay, April 1st snow water equivalent equates to this stream flow volume in the summer. Shorter term forecasts are typically based on temperature index models. So we start with a accumulated volume of snow, look at the measured air temperature, and then with a calibrated model, predict how much snow is going to melt and run off. Either one of these systems is dependent on the period of record, and implicitly is dependent on this year being a lot like years that we have seen in the past. Increasingly, that is not the case. So these type of systems, no fault of their own and no slight to the very capable folks running them, these type of systems are bound to encounter failures as we move further and further from the conditions that we've experienced in the past. And I could talk for hours about all of those items on the bottom left that are forcing us into a different environment. So the question, and this is critical because managing our water supply depends on an accurate forecast. And just one example here from the city of San Francisco's Hetch Hetchy operation. This reservoir provides water and power to the city of San Francisco and a bunch of users on the peninsula. They have one source of input to the reservoir, that's snowmelt. It barely rains at all in the summer there. And then they have at least 3 competing management goals: in-stream flows for ecology and other downstream users, power generation, which if they fail to meet, they have to buy power on the open market, which is very expensive, and then water supply, of course, obvious ramifications if they miss that. So this better information on snowmelt and inflow to the reservoir can produce much better outcomes and optimize their management. So how do we add resilience to those forecast models that are suffering from changes in the environment? The first is to decrease the reliance on the historic record. So pull back a little bit and say, okay, well, we don't need to know 30 years of record for our statistics. We can actually look at the conditions on the ground now, improve the model realism such that they're responsive to those physical processes. To do that, we need to increase the availability and use of spatial data. So data that covers the entire watershed, not just a single point measurement. And this can be satellite, airborne data, as well as improved mesoscale and refined mesoscale weather models. 2 things we have going for us. One is that the accumulation of snow across the landscape is the primary driver of where and when it melts. So if we have, for example, if all the snow accumulated on north-facing slopes, it would melt out a lot later because those slopes are shaded until later in the season. Related to that is that solar radiation is the primary driver of snowmelt, not air temperature. The air temperature models work because it gets warmer when the sun comes out, so we're using this sort of proxy variable. But really it's solar radiation that's doing the bulk of the snow melting, except for maybe on the Olympic Peninsula where it's all cloudy. But we have the capability to monitor these 2 things operationally with remote sensing technologies. And that's where we've come up with the Airborne Snow Observatory. So we fly a similar payload to NEON, as well as the Carnegie Airborne Observatory, scanning LiDAR and a spectrometer. And we get snow water equivalent by mapping the difference in elevation of the landscape with snow on it and snow off of it. That gives us snow depth, which is the primary driver of water equivalent variation across the landscape. We get to water equivalent by measuring and modeling snow density. And then we get snow albedo from the spectrometer as well. We started this program in 2013. Actually, the first flight that ASO conducted was a NEON flight with their initial payload in southern Colorado. So there's even some co-legacy in those two programs. I'm using an example of the Tuolumne River Basin here. Again, that's Hetch Hetchy Reservoir at the lower end of it. And I should have 2019 on here now. We've got 6 flights this year. They've been great partners in exploring the utility of these data to their operational system. We've been refining our processing to get fast turnaround data delivery. Data latency is really important with the snowpack since it can change on a very rapid time scale. And then neighboring basins have been watching quite intently, and we are now flying quite a few more. So we've been able to generate this total basin aggregate snow water equivalent volume multiple times through the melt season for multiple years, spanning the driest year on record, 2015, through the wettest in 2017, and some years in between. And we've had an impact. The bottom left figure is a regression on ASO measurements of total SWE volume versus the actual measured inflow to the Hetch Hetchy Reservoir. And we've got a 0.987 R squared on that relationship. So as a water manager, this is awesome because you can say, okay, well, we got a number out of ASO. Regardless of some variations, we're going to have a pretty good bead on the total water coming into our system through the end of July. And importantly, we're seeing snow that is not seen by the traditional observation network. So on the upper right here, we can see the trace in the background. The time series curve is the snow as measured by in situ snow pillow stations on the landscape. Those melt out sometime in April, and yet ASO is still seeing all of the snow that exists at elevations above those sensors. So it gives the proximal and primary information that water managers need. And we've had a great response from our partners. So to date, we've been flying predominantly in the Southern Sierra, six major river basins there. We have a paired snow modeling effort with the Agricultural Research Service in Boise, Idaho, to provide daily updates in between the flights. So we're using the ASO data in that model assimilation framework. And I'm only showing the Sierras here, but we've got several basins in Colorado that we fly regularly as well. In the future, we're going to continue monitoring the Southern Sierra, and within 5 years, the plan, this is the state of California's plan, is to build this program out to fly the entire snow water resource in California. So this is pretty exciting, but it comes with a whole bunch of challenges. We've got data integration challenges with the existing California data sets, as well as what we're used to doing, and then plenty of synergies with auxiliary and adjacent managers. So if we think more broadly about this, the ASO is kind of emblematic, I think, of this broader spatial revolution that's happening. We're moving away from or moving beyond just in situ data to having regular access to high resolution, broad extent data sets. In this case, it's LiDAR derived snow depth, but we've seen other examples in the past 2 talks that this is really an industry-wide thing, if you will. And importantly, these data are moving from the research realm and into operational availability with latency and data accuracy and resolution all becoming operationally relevant in terms of time scale and data production. This revolution also provides a bunch of new data challenges, some of which we've heard already. I'm going to echo a couple of points that we've heard and put a finer point on some of them. The research and operations divide. So a lot of times we use the same data source for either a research endeavor or an operational endeavor. But it's rare that the data source is designed to support both of those. So research data streams tend not to be consistent in time, or they change over time as the goals of the research project change. It's difficult to find sustaining funding to keep those going. Whereas operational systems are usually targeted at one particular engineering goal, if you will, and don't commonly, if I can generalize, capture a full range of process variables that are necessary to explore the physical system. So there's two different kinds of questions that get asked, if you will, by a research project studying the physical system versus an operational product. And I think it's really important to not only recognize those, but look at linkages between them. How can we use study of the physical processes to inform management goals and vice versa? Project scale, the previous two speakers mentioned this as well. You know, if you're doing data management for a single flight or maybe a single campaign year, you can probably wing it. You can probably have your technical staff generating the metadata retrospectively. You could probably pull it off. But when you start moving into bigger areas or longer terms, you've got changes in instrument configuration, changes in processing, and we've heard some of this already. Without an a priori strategy to manage the data coming out of a more complex project like this, it's going to be painful for the data producers, I'm thinking, and it's not going to serve the end user very well. So how do we expand data use? There's a lot of, this is a far from a comprehensive list, but here's a few ideas, some of which we're doing, some of which are recognized and happening elsewhere. It's important to think, I think, about how data are organized. So we're talking here about an airborne campaign, so that you could call maybe a longitudinal data management approach, where it's a single airborne project and has multiple instruments, multiple levels of data, et cetera. We could also think about a latitudinal approach, and this is kind of how the data formats get generated, where it's just looking at LiDAR data, for example. So LiDAR data's got kind of its own unique format or suite of formats that are usually sort of consistent. And so maybe a LiDAR user would be looking at this airborne campaign and that airborne campaign and that drone campaign and some ground-based stuff, and they're interested in commonality of data formats that way and looking to extract that from this particular campaign. So I think we want to think about supporting both of those approaches, both on the campaign scale as well as latitudinally with the instrument. I've identified a role for data centers in the last bullet here, but I think I could have put that sub bullet on every one of these. Data centers, I think, are really important in terms of providing resources to either new or sustained airborne programs. So I'll close with this. I want to invert the problem and say, what if an airborne program was designed with a diverse set of data users in mind from the start? And I don't know about every airborne program out there, but every one that I've seen is designed with a particular use case in mind, and sometimes even that's not very well defined. And then later on, we get other people contacting and saying, hey, I want to use your data for this, and it becomes incumbent upon the program to try to help support that. So a few key enabling things here. We can't assume knowledge on the part of the data user that we just know implicitly. We make decisions on the fly, whether it's when we're integrating instruments or whether in the data processing design. We can't assume that the end user down the line or 10 years down the line is going to know that stuff. The decision making in that whole process from design through execution needs to be transparent and documented. And the third point, it's got to be enabled by funding support. So we can't just go into an airborne program and say, okay, we're going to do this and not have data management support from the get-go. We've got a couple examples at NSIDC where it's like, okay, we got invited late to the party, and it ends up being pretty painful for everybody. I'll just concentrate on the last bullet here. I've got an email sitting in my inbox right now that I can't reply to because they're asking about data that we've had in Colorado starting in 2013, and our processing and instruments have evolved over that time, and I can't just give them the data. It has to be a collaboration at this point. We can't go back and reprocess everything. We don't have the staff to do it. If we had designed everything from the get-go with a diverse set of users, standards, if we had support to do it, the impact on our technical staff would be much reduced, and the data user would already have data in hand right now and probably have a paper out on it. So I think this is a great conversation that you guys are fostering. I really want to see it continue, and I want to thank the other speakers as well for really tying it all together. Thanks.
Great, thank you, Jeff.
And I agree. NASA is now starting to get the DACs involved early in those investigations to help get that data to be more useful. Chung-Lin, one question while we transfer, and then we've got to keep moving.
Yeah, Jeff, very interesting. You for this topic here, you're focusing on the snow, right? But you also taking care of the ice. For instance, this ice bridge. Is that data also being issued by your center? Ice bridge. Right,
Yeah,
do
the
you-
ice bridge data is also at
Sure.
NSIDC.
So basically, for the snow ice data, you probably experience same kind of challenge, or same kind of problem. Are they similar? For the ice okay data and the snow data.
I think I caught most of that. The hammer drill is going on there at the same time.
He said for ice and snow, are you facing the same kind of challenges in the data?
Yes, I mean, there's some nuance in terms of using similar instruments over different targets. But yeah, I think, the big lesson that we learned but were unable to implement from IceBridge is that, planning your data as your data management as you're planning the data acquisition is really the best and most efficient option. But the ASO kind of spun up on a shoestring. We cobbled together NASA headquarters funding, terrestrial hydrology program, some infrastructure funds at JPL, and there was no go-to rah, let's do the data management opportunity right there. So we basically had to cobble it together. Yep. And who knows, the program could easily have died after 6 months. We didn't have sustaining funding from day one. So it was kind of difficult to argue for a big data management approach at the same time. So we're kind of battling a chicken and egg problem.
Well, thank you, Jeff. And
Thanks.
We're going to move on. So these first three were on the topics, and now we're going to turn to technology. And Helen Conover, who is leading the Visage program for the past couple of years, is going to show us what they've been doing with it. And there's some various tools, FCX, which was at GHRC DAC, and the Visage improvements. So thank you, Helen.
Okay, hi folks. I'm from the University of Alabama in Huntsville, and I've helped coordinate 2 of these programs. The FCX and Visage, and Simba is a data merging type thing that we're looking at in Visage. And so in the interest of time, I'm going to go through this pretty quick and just kind of show you a little bit about what we've got and kind of point out the unique things about each one of these. And the reason we wanted to talk to you about some technologies today is to kind of spark some ideas about what might help in making these data more usable for more different kinds of users. And if I could get feedback from some of the science folks about, are these things the kinds of things you'd like to see? So, because one of the things we want to come out of this group is focusing resources on things that will help the communities better. So the first thing, the Field Campaign Explorer, it's was built to help with the Hurricane Severe Storm Sentinel, which was from the first generation of EVS projects from NASA. The thing that it does that most of the other similar tools don't do is it integrates flight reports as well as the data into this whole system. Visage is more about 3D visualization, interactive building of the 3D data to look at and interacting with it. It's cloud native, so you've heard a lot about cloud this week, and as more and more of the data are going to reside in the cloud, then these kinds of architectures will help use these data more quickly. And then Simba is a data integration tool that interpolates a lot of different products onto the same 3D grid. So here's FCX. I will point out these are the images from the flight reports, and they're time tagged and space tagged. So as the plane is flying along in the viewer here, these are the images that correspond to what the plane's seeing. And then you can, from this tool, you could access the mission reports, you could access the data, and The thing about these field reports is that they're unstructured. These were at least digital and not handwritten, but it took a lot of graduate student time to go through and pull the images and time tag them and that kind of thing. So what we're doing now, this is at the GHRC DAC, is taking that, I'm calling it a legacy application. It's 3 or 4 years old, and porting it to a cloud native architecture. The new focus right now is the GOES-R post-launch test field campaign that happened maybe 2 years ago now, yeah, in 2017. So we're kind of up, as part of updating the tool, we're also bringing in additional kinds of data. And the hope is that since it's going to be cloud native and it's going to be cloud resident, and a lot of the NASA DAC data is moving into the cloud, this will be widely applicable. And it's, you know, we'll be able to display flight tracks, visualize the data, and provide download links to those data. So Visage is my project. It's currently, we're getting toward the end of a 2-year funding cycle from AIST. You can see the screenshot image has got a lot more going on than the older FCX one. And we're looking mainly at 3D visualization, which is, it's fun to play with. And these are built on the fly and users can interact with them. And we have a cloud repository. And again, we're working in precipitation with the precipitation measurement team. Okay, we can go through this pretty quick. GPM ground validation was a series of about 6 years of precipitation validation, looking at the satellite validation, but also at process studies. And what we're focusing on in this project is golden cases where we have a lot of instrumentation operating and we have interesting weather and the GPM core observatory is passing overhead. And so that gives us a lot of good material to look at and see how it works together. Here's the use cases. You can see the one is local Olympics. Here is technical challenges. Primarily, we're looking at 3D visualization. We're looking at different visualization engines. We're looking at different ways to render 3D data. Spent a lot of the first year trying different things and seeing what was both feasible as far as cost and time and also usable by people. And temporal alignment is fun. And it's all built in Amazon Cloud technologies, serverless technologies for the techies here. We will see if the demo will work. Yay. Make her big. So this is a airborne radar type instrument. It's called HIRAP. We're looking at, it was just looking nadir for this, but you can see how when the plane shifts, the angle is changing. We can speed it up by the clock. We have various different other data. These are dysdrometer type rain gauges, and you can see them changing in size, height, and diameter with how much rain is happening. This is the GPM satellite radar merged with ground radar. So you've got the ground radar footprint and the satellite radar little vertical things. We're showing the flight track and we're showing a 30-minute lag on the HIRAP data. And I'm trying to decide if I should let it run for the whole 2.5 minutes. This is the eye candy part, so it's fun. This is Olympics. Yes, this is the Olympic Peninsula. And they're about to, oh, if I knew how to run this better, I could speed it up. These cubes here are the SIMBA data, and this is rays from a radar in-pole radar that's sitting there. We are running on the cesium platform. These are 3D tile point clouds that we're looking at. And there was a Python library that came with cesium to do this, and we built our own Java. This is a spatial subset of 3 different kinds of data: the radar, the validation network, and the Simba column. This is a browser. The window we're seeing is a browser, and the server is out in the cloud. And it's memory intensive, and we're working on that. And we don't care about these guys, do we? So we showed you in the demo these columns getting bigger, taller, or wider, depending on the aspect of rain we were looking at. You can also pop up a little graph window that shows you different, you can pick which aspect of the rain you want, and it moves in time as the data moves in time. So that's kind of fun. And then we're doing some basic analytics. The idea is that you can, the data access API is used to build those graphics. They can also bring you, you can subset the data or generate histograms or basic statistics. And what we are aiming toward is being able to compare data across different observations of the same thing. Okay, so what about Simba? Simba was building those atmospheric columns. It's combining the satellite data, the ground-based data. It's primarily looking at various different radars, but also other sensors. The user can specify the grid. It encodes everything in a net CDF file. It maintains the attributes of the original data, but then brings it all into a common 3-dimensional grid. And so how does that relate to airborne data? Well, today it doesn't, but because today they're doing the satellite and the ground, but they're trying to figure out the best way to bring airborne data into these columns and what the payoff is going to be there. So, so that's being strongly considered. And so if people think that something like Simba is really cool and having airborne data in it too would be really cool, we'll feed that back to the developers there. Okay, Deborah, I know you wanted to have some time to do an activity, so you got 15 minutes left.
Does anyone have any more questions for Helen while we're switching?
She's gonna make it so we have some more time. And oh crap, how do you do this? Pick up slides. Where? Oh. I haven't paid attention at all to this. Oh, here we go, back up, I see it now. Here we go.
You got it.
Got it.
Yours are probably still up.
I want to go back to the slides so we can look at the, expand it. There we go. Got it. There we go. So we have some group discussion, which we won't do as a group now because we're running a little behind. But we really appreciate, in fact, they join me in thanking all the speakers because I think that was really valuable to hear. And for many of them, it was their first time at ESIP, and I think that's really valuable that they were able to come and hear a week full of data science folks doing their thing. So we have some group discussion questions up here. I'm going to buzz through them, and then Amanda's going to lead a discussion because my voice is going to give out. In fact, I'm not even going to read these. But before you all leave, because I know everybody's itching to get out, I do want to do this really quick. We're going to follow this initial conversation up with a session at AGU. By the way, deadline July 31st, don't forget. And the first one is the one I'm leading, which is an e-lightning session on airborne data to kind of further this conversation and keep getting ideas out there and find these issues and figure out solutions and steps forward. So that's going to be fun. If you've never done an e-lightning session, I'll help walk you through it. I've not done it myself, but I saw one last year and I was so jazzed because it was really a great way to have a conversation. And then also we have the next session is session IN 047, and that's tracks across the sky. This is primarily dealing with any kind of data set that comes in a track, be it ship, airborne, field moving along, taking samples, whichever, a boat along a stream. So that one's going to be really interesting, followed by some metadata quality issues in IN 014. That's not just dedicated to airborne, but airborne is going to be in there represented. And session IN 036, which is making moving small science instruments and their data fair, and that's looking at drones, which I'm really curious about, which are airborne. Let's not forget. So go back to group discussion. Thank you. Amanda.
So we don't have enough time to go through all of these questions, but I did post them in the minutes, the meetings page. So the notes page. So if you have thoughts on any of them that we don't talk about, feel free to jot them down there. So there's quite a few different things we were trying to tease out here, partly just what kind of interest is there in continuing this. I guess I'm just going to start with a question I have to get it rolling. We heard a lot about the need to link between different data types, satellite, airborne, ground. So very multi-dimensional linkages, not a clean, like we must link this to this. I'm curious if Heather or any of the other speakers are using, so Helen, you talked about you're moving it into an analysis ready kind of data cube, but I'm wondering if anyone else has been looking at different techniques for providing this linkage between all these different elements, dimensions, data types.
So Simba was a way to kind of pre-generate a cube of data from multiple instruments all in the same space and time. What I didn't talk to you about in Visage is we're bringing all the data from its diverse formats and things and pulling it into an analysis optimized data store in the cloud so that then it's easier to pull out the sections you want of each different kind of data. And what we showed you was the visualization because that's where we're focusing. But of course, those kinds of data stores can be used for all kinds of analysis. And so, pulling data from its own native formats into the cloud in a common format is one approach. I'll say one more thing. There's a lot of data out there in its own native formats that everybody that uses that data knows how to use, and they have a lot of good tools. And you bring something from a radar format into NetCDF, it's more standard, and a broader community can understand how to look at those files, and all those tools may not, you don't have the same library of tools. So there's hazards too.
That last one is a great point. I want to follow up on that a little bit. One issue, and I'll use an example from IceBridge actually. A lot of different radars on the IceBridge platform, and they were all, they have a community of users that use this MATLAB toolbox, and they were pretty much plug and play, mainly because the CRESIS program, which was at University of Kansas, had developed all this, and they had a broad user base. Well, we're trying to bring that into NASA data standards. MATLAB is not, .mat files is not an approved NASA data standard. To their credit, the CRESIS crew convened a community-wide effort to push those data into NetCDF and produce translators and readers to and from their MATLAB tools to do this. So they recognize the value of the data standardization effort, but also recognize that they needed to connect to existing tool sets. And so this is, more broadly, any effort, I think, to standardize and make things play nicely together amongst different platforms can't lose sight of the end users, the primary end users that may be used to a particular data type. And so there may need to be development and outreach efforts that go along with that to say, okay, I know you're used to using X platform to process your ship track, sonar data, but if we all get together and do this and use this new tool, here's the myriad of other opportunities that come with it. Data integration, similar issue with NEON. When you use a hyperspectral instrument, you have a data cube of all those different spectral bands, plus at the spatial resolution. And then you could do that through time as well, and that inflates rapidly, volume-wise as well as data access-wise. Trying to integrate the LiDAR-derived data with that can be extremely challenging, especially if you're trying to just wire it together kind of off the cuff. Some efforts exist to try to do this. The GRID program run by the U.S. Army Corps, leveraging some of the tools that Helen showed, Poetry and whatnot, has been focused on LiDAR data, but also allows many different data types to be tagged to individual points as attributes. So you could tag a vector through a hyperspectral cube to an individual LiDAR point and access it quickly through their system. Again, it's targeted at a particular type of user. It was developed with military applications in mind, but it's all open source and it's quite useful for geospatial data, and is a program of record now with NGA and USGS and Forest Service are using it and whatnot. But again, I mean, how many people have heard of GRID? Poetry, GRID, because yeah. This has seen 15 million, probably more now, dollars of development over the past decade, and it's fantastically capable. But if you're not plugged in one way or another to it, you don't know about it. So I think that is another topic, is bringing that different tools to bear to the broader community.
So speaking of user communities and formats, Heather, I was wondering if, since you're serving these different communities, are you guys having to tailor your data formats or what you're providing them to address that? Like, just curious a little bit more about how you're serving these different users who might have different needs.
So far, we haven't done a whole lot with changing the way that we format our data, but we want to move towards more NetCDF based formats, since that's the more popular and easier way to add metadata and whatnot. But so a lot of our real-time users are just getting the data off of the GTS. So we don't really have any control on that so much. We have made a change to providing additional formats for models recently, but we are definitely trying to keep in mind, what was just brought up, and that some of our main users are comfortable with a certain type of format, and so I've worked with several scientists recently who have been in the field for a while and seem afraid of NetCDF. And so we're definitely trying to keep that in mind as we trying to decide what we want to do with our data formats. But I've seen some tools like ERDAP where you can provide it in a certain format and users can pull it in whatever format they want. So a tool like that seems like a really great thing to use.
I should clarify that ERDAP is a server, so pretty much you rely on someone to set up the server for you. You can put the NetCDFs in it and have ERDAP serve them out, or also ERDAP will integrate with an OpenDAP server if you want to do tricky things like aggregations and such.
Yeah, I mean, I just wanted to say, I mean, we tried to use standardized data formats as best we could, particularly GeoTIFF for most of our higher level data products, and then, LAS and LAZ files for our LiDAR. We kind of had to go off the board with our reflectance and radiance files and go with HDF5 because there was no really good existing format for storing that data along with all of the metadata that we thought needed to be with it. And so there have been times certainly where we have felt like we have force fed our community an HDF5 format that they were not ready to use. But I think we did our best to provide tools and educate them on that use, and eventually it's going to come around.
Was it because there was metadata inability to handle the kinds of metadata you felt you needed to store?
Correct. Yeah, I mean, there's a lot of information associated with the atmospheric correction that we
Yep.
do for our reflectance that we wanted to include, particularly ancillary rasters that weren't necessarily the reflectance data.
So I'm hearing there needs to be some work in the metadata world to help
Yeah,
accommodate the kinds of detailed metadata that this community needs.
yeah, and I would say one of the primary challenges we had is, storing the raster data in the HDF5 format. Most geospatial software would be able to find and read the reflectance data, but was obviously unable to find where we stored the mapping information to properly geolocate the imagery.
Yeah.
And so, that was the main problem that needs to be overcome. So, I mean, obviously, if there's a standardized place to put that information in an HDF5 format, then.
Thank you. Can I address in number 4, question
Yes.
4? All right, okay, great. Before I addressing that, can I have a question? For all this, the airborne data, do we have a DOI for all those data sets, right? We do have, right? Okay, great.
Yeah, I can't hear because of the pounding, sorry.
Well, do we have, all the data have a DOI?
Oh, well, yes.
Okay,
DACs are
Good.
doing so as they
Sure.
publish. And then
I
there's a
just-
whole slew of
okay,
airborne data that's not
great.
published, and that's what ADMG is working
Sure.
towards getting
I-
that data
yeah.
published.
I just share as a previous scientist, when I using the airborne data only when I try to validate the satellite data. I at the time studied the rainfall using the trim data. So I had time using the campaign data at the time. So I think probably the challenge is here. For all the campaign itself, they already serve certain purpose. Probably only serve to certain group. And also usually they are local, only at one point data there. And also short period of time. So I think probably that's the challenge. So I don't think would be so say, well, the user is not so much as the set data. I think that's the nature of the data itself, right? So you don't expect the people using too many observation data, sounding data, or the campaign data than the satellite data, because satellite data or even the numerical data like MERA2. Actually, MERA2 is the most popular data in our data centers here. So I think we are. So I would probably address more try to. The reason why I'm joining this group again, to attend this one, I try to, because recently I'm involved in the data quality paper documentation. And one of the reviewer kind of criticized the paper, the documentation only emphasized remote sensing, the satellite, and not about the airborne data. So that's why I try to come back to here to see what's really the challenging for and even so, I think the challenge for this campaign data even is that data quality, right? It's because it's more complex. It's so many variety for different campaigns.
Right, these data sets are so heterogeneous. So are you saying, Changling, are you asking, are we doing DOI? We're doing DOIs on a data product, like individual data product, which is often usually that data that comes from a particular instrument that flew in that campaign. Are you asking about a DOI for the entire campaign so that one could refer to all the data in that campaign?
Well, I'm not particularly mean the later one. I mean, okay, for this campaign, yes, indeed, like this campaign, how do you refer to a DOI for those data? Say if you assign DOI, when you only go to the landing page of that data set, like Icebridge, you have several lags. Are you going to have a different DOI for different lags, or just include the period time you have a one single DOI? Or
Well, Icebridge is all at NSIDC, but we, as Helen mentioned, or Deborah mentioned, we are minting DOIs, just like satellite, we're minting DOIs at a product level, an individual data product or data collection, depending on your nomenclature. So I know there has been some discussion about if you want to represent a DOI for all of the LiDAR products collected within an Ice Bridge campaign, how can you cite those? But we're not at this point minting. Yeah, yeah.
And,
I think-
GHRC is doing DOIs for the entire campaign. Like the Olympics campaign has one DOI. So that if someone used all the data in the campaign in their paper, they can say, cite one DOI for the entire campaign.
I beat you to it, Beth. Yeah. Identify early and identify often. That's the rule. But anyway, on the HDF5 and NetCDF4 thing, what can make either of those formats less scary is the community conventions that you use when you're writing the data and the metadata into those files. And both of those formats can actually support multiple conventions. But if you're thinking about writing some NetCDF, you should really pay attention to the climate forecast conventions and the attribute convention for data discovery. And it was that second one was a topic dealt with in ESIP in the documentation cluster a couple of years ago. So because then that makes the usage of those data with standard tools much easier. So that's a really important thing to understand on the way to NetCDF and HDF land.
If I can bring it back out a bit from down into the weeds of HDF and NetCDF, I can say that I understand why scientists are scared of NetCDF. To them, having to know all the metadata standards is something they don't typically deal with and they don't have a lot of time for. And so that's where a good relationship between a DAC and the scientist producing the data is really, really important, because it's about communication and education of that. How do we help you get this done?
Well, and as we heard from some of the speakers, there aren't necessarily data managers working on these airborne projects. There maybe wasn't funding to even embed that in the project. So that barrier to creating those standard formats is higher when you don't have people who can dedicate their time to it. Do we want to, we're at time.
Are we?
Yeah.
Well, I certainly want to thank everyone for staying to the very, very end and appreciate your input. And I hope you got something out of this session and an awareness of airborne data issues and the concerns. And we hope as we go forward, we can keep this conversation going. I hope to see you at AGU. That would be great if you have a contribution. Please put in an abstract by the deadline, and we look forward to any more conversations. Maybe we'll be back next summer at the ESIP and really get a good session going, not on the last session of the week. Thanks.